Okay, yesterday we were discussing about component form of vectors. So let us recall the main concepts we had learned in this chapter. P, X, Y, Z be a point. Then the position vector of P is OP, which is denoted by R, vector R. It is given by xi plus yj plus zk in component form. Here x, y, z are called the scalar components, and xi, yj and zk are the vector components. Okay. If vector A is given by a1i plus a2j plus a3k, then modulus of vector A is root of a1 square plus a2 square plus a3 square. See, this is in component form. Vector A is equal to a1i plus a2j plus a3k, and modulus of A is equal to root of a1 square plus a2 square plus a3 square. If this is equal to 1, that is modulus of vector A is equal to 1, this is a unit vector, and therefore if this is equal to 1, then vector A is a unit vector, and therefore a1, a2, a3 are the direction cosines, are called the direction cosines. Otherwise we call this as a2, a3 are the direction ratios. Is it clear? Please respond. Is this clear to you? See, P is a point xyz having coordinates xyz. The position vector of P is given by vector R is equal to xi plus yj plus zk. This is in the component form. Similarly, a vector A is equal to a1i plus a2j plus a3k, where modulus of A is equal to root of a1 square plus a2 square plus a3 square. If this modulus is equal to 1, this is a unit vector, and hence a1, a2, a3 are the direction cosines. Otherwise, we call this a1, a2, a3 as the direction ratios of vector A. Okay, now a unit vector in the direction of vector A is given by vector A by modulus of vector A. A cap is equal to vector A by modulus of vector A. Unit vector denoted by A cap can be determined by dividing the vector by its modulus. A unit vector in the direction of vector A is given by A cap is equal to vector A by modulus of vector A. Now let us move to the next one. Vector joining 2 points. Next heading, vector joining 2 points. Let P x1 y1 z1 and Q x2 y2 z2 be any 2 points. Then vector PQ is given by x2 minus x1I plus y2 minus y1j plus z2 minus z1k. So the vector joining 2 points, here the initial point is P and the terminal point is Q. Therefore, the coordinates or the scalar components here x2 minus x1, y2 minus y1 and z2 minus z1 are the scalar components of vector PQ. So if you are given 2 points P and Q, then to write the vector PQ in component form, x coordinates here x2 minus x1 gives the scalar component along the x-axis x2 minus x1 I plus y2 minus y1 j plus z2 minus z1 k. And the modulus of PQ is given by modulus of vector PQ is equal to root of x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. This is the distance formula you had learnt in 11th standard. Distance between 2 points P and Q. Is the modulus of vector PQ, which is root of x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. Now the next one is section formula. The position vector of the point R which divides vector PQ internally in the ratio m is to n is given by the position vector of r. Position vector of the point r is denoted by vector r. This is equal to m b plus n a by m plus n. Position vector of the point r which divides the vector pq internally in the ratio m is to n is given by vector r is equal to mb plus na by m plus n, where b is the position vector of q and a is the position vector of p. This also you had learnt in 11th standard, section formula in coordinate geometry. Here we are writing this in terms of position vectors. That's the only difference. You are writing the coordinates there, mx2 plus nx1 by m plus n, my2 plus ny1 by m plus n, mz2 plus nz1 by m plus n. That's what you had learnt in 11th standard. Here we are writing the corresponding position vectors. So vector r is equal to mb plus na by m plus n. If r divides pq externally in the ratio m is to n, then the position vector of r given by vector r is equal to mb minus na by m minus n. Is it clear? Now the third one here is, if r is the midpoint of vector pq, then the position vector of r is given by a plus vector b by 2. It is vector a plus vector b by 2. M is to n becomes 1 is to 1. 1 is to 1 here. 1 into b plus 1 into a by 1 plus 1. That is a plus b by 2. Let us now move to exercise 10.2. First one, compute the magnitude of the following vectors. Compute the magnitude of the following vectors. First one, vector A is equal to I plus j plus k. So if vector A is equal to a1i plus a2j plus a3k, modulus of vector A is given by, or the magnitude of vector A is modulus of vector A, which is given by root of a1 square plus a2 square plus a3 square. So the magnitude of vector A is given by modulus of vector A. This is equal to root of, here a1, a2 and a3 are equal to 1. 1 square plus 1 square plus 1 square, which is equal to root 3. Okay, now the second one. 2i minus 7j minus 3k. 2i minus 7j minus 3k. Find the magnitude. Find the magnitude and give your answer. Okay, it is root of 62. Now one more question. Vector C is equal to 1 by root 3 I plus 1 by root 3 j minus 1 by root 3 k. Find out the magnitude of vector C. So it is 1 by 3 plus, that is 1 by root 3 the whole square plus 1 by root 3 the whole square plus 1 by root 3 the whole square. That is 1 by 3 plus 1 by 3 plus 1 by 3 gives 3 by 3, which is equal to 1. Okay, so here see, in this case the magnitude is root 3. Magnitude of this vector is root 3. So the scalar components 1, 1, 1 are the direction ratios. We call the scalar components here as the direction ratios of vector A. Here in this also, the modulus of vector B, that is magnitude of vector B, is root of 62, which is not equal to 1. So the scalar components 2, minus 7, minus 3 are called the direction ratios. But here in this one, see, the modulus or the magnitude of the vector is equal to 1. Therefore, this 1 by root 3, 1 by root 3 minus 1 by root 3 are the direction cosines of vector C. In this way, you can identify whether whether the scalar components give the direction ratios or the direction cosines. If the magnitude is equal to 1, it means this is a unit vector. If this is a unit vector, the scalar components are the direction cosines. If it is not a unit vector, then the scalar components are called the direction ratios. Now the next one. Write two different vectors having same magnitude. Write two different vectors having same magnitude. See, I will write a vector here. Vector A is equal to 3i plus 2j plus k. So you have to get the same magnitude here. Same magnitude means the square of the scalar components will be the same. Okay, for that let us write another vector B, I plus 3j plus 2k. This is a vector whose magnitude is same as this one. See, magnitude of vector A is root of 3 square is 9 plus 4 plus 1. It is root 14. Similarly, here in this vector B, this is equal to root of 1 plus 9 plus 4. Again it is root 14. Magnitude will be the same. Can you give another example? For this vector A itself, magnitude remains the same. For vector A, write another vector with magnitude same as that of A. Give an example. Here it is, write only two vectors, but let us try another one. Vector C. It is 2i plus j plus 3k. 2i plus j plus 3k. You can form another one, 3i minus 2j plus k. That's another vector. Or you can write this as minus 3i plus 2j plus k. That will give you another example. Okay. Moving to the next one. Write two different vectors having the same direction. Write two different vectors having the same direction. So let us consider A is equal to 3i plus 2j plus k. Then the definition of scalar multiple of a vector. Scalar multiple, that is lambda A is a vector which is collinear to vector A. Collinear to vector A. Also it is given that if lambda is positive, the direction of vector lambda A is the same as that of A, and if lambda is negative, the direction of lambda A is in opposite to that of vector A. So can you give an example? You can write any scalar multiple here. That is multiplying this with 2. 6i cap plus 4j cap plus 2k cap. This B is a vector which is in the same direction of A. We are multiplying this with 2. A scalar multiple of vector A. 3 into 2, 6. 2 into 2, 4. 1 into 2, it is 2. So vector B is a vector having the same direction of vector A. If you multiply this with a negative number, that is if you are multiplying it with minus 2, then we are getting a vector which is having opposite direction of A. Having direction opposite to this vector A. Is it clear? Okay. Now the fourth one. Find the values of x and y so that the vectors 2i plus 3j and xi plus yj are equal. Find the values of x and y so that the vectors 2i plus 3j and xi plus yj are equal. We had learned in the properties of vectors, two vectors are equal only when their scalar components are equal. Corresponding scalar components are equal. So what are the values of x and y? It is x is equal to 2 and y is equal to 3. Now the fifth one. Find the scalar and vector components of find the scalar and vector components of the vector with initial point to 1 and terminal point minus 5, 7. Find the scalar and vector components of the vector with initial point 2, 1 and terminal point minus 5, 7. Let P be the initial point 2, 1 and Q be the point minus 5, 7. Then vector PQ is given by when 2 points are given. How can you write the vector? Distance formula is to find the modulus of this vector PQ. Just you have to write this as minus 5 minus 2i. This is x1 y1 and this is x2 y2. Okay, so this is minus 5 minus 2i, then plus 7 minus 1 j, which is equal to minus 7i plus 6j. So which are the scalar components here? Scalar components minus 7 and 6. And the vector components minus 7i plus 6j. See, if you have to find the modulus of this vector PQ, then you have to use the distance formula. You can apply distance formula then. Or it is root of 7 minus 7 square plus 6 square. So here 2 points P and Q are given. To write the vector, what we have to do is x2 minus x1, that is coordinates of this Q, that is to be considered first. x2 minus x1i plus y2 minus y1j. Okay, now the next one. Find the sum of the vectors vector A equals I minus 2j plus k I minus 2j plus k. B equals minus 2i plus 4j plus 5k, and vector C equals I minus 6j minus 7k. Find the sum of the vectors. Vector A equals I minus 2j plus k. Vector B equals minus 2i plus 4j plus 5k. Vector C equals I minus 6j minus 7k. To find the sum, we have to add the corresponding scalar components. To get the sum of this, to add these vectors, add the corresponding scalar components. So, vector A plus vector B plus vector C. Add them and give your answer. Okay, adding this, I minus 2, here 1 minus 2 plus 1. So it gives 0i, then minus 2 plus 4, this gives minus 4j, then 1 plus 5 minus k. Or you can write this as minus 4j minus k. Okay, next one. Find the unit vector in the direction of A equals I plus j plus 2k. Find the unit vector in the direction of A, which equals I plus j plus 2k. So the unit vector in the direction of vector A is denoted by A cap, and this is given by vector A by modulus of vector A. So which is the answer? The unit vector in the direction of vector A. It is 1 by root 6, which is the modulus I. 1 by root 6 I. Here the scalar component is 1. So 1 by modulus of A is root 6, that I, plus again the scalar component is 1. So it is 1 by root 6 j, plus the scalar component is 2. 2 by root 6 k. This is the unit vector along the direction of vector I. Okay, the next one. Find the unit vector in the direction of Find the unit vector in the direction of vector PQ, where P and Q are the points. P is 1, 2, 3 and the point Q is 4, 5, 6. Find the unit vector in the direction of PQ, where P is the point 1, 2, 3 and Q is 4, 5, 6. So first you have to write the vector PQ. Give the answer. What is PQ? 4 minus 1, which is 3I. Then plus 5 minus 2, again 3, 3J, plus 6 minus 3, 3K. Then PQ cap, the unit vector in the direction of PQ is here it is 3 square plus 3 square plus 3 square. Root 27 I, then plus 3 by root 27 J plus 3 by root 27 K. Now the next one is, if vector A is equal to 2I minus j plus 2k and vector B equals minus I plus j minus k, minus I plus j minus k. Find the unit vector in the direction of vector A plus B. Find the unit vector in the direction of A plus B. So first you have to find A plus B, vector A plus B. It is A is 2I minus I, which gives I 2 plus minus 1, then minus 1 plus 1, it is 0j, then plus 2 minus 1 plus k. Vector A plus B is I plus 0j plus k. Let us represent this as vector C. That is A plus B is equal to vector C. Now a unit vector in the direction of A plus B is denoted by C cap, which is equal to modulus of this vector is root of 1 plus 1. So it is 1 by root 2 I plus 1 by root 2 k. This is a unit vector in the direction of A plus B. Okay, now the next one is find a vector in the direction of Find a vector in the direction of A equals 5y minus j plus 2k, 5y minus j plus 2k, which has magnitude 8 units, which has magnitude 8 units. A vector in the direction of vector A with magnitude 1 unit is the unit vector. Okay, so it is, let us first find A cap. This is equal to 5 by modulus of vector A is 5 square plus 1 square plus 2 square, root 30. So it is 5 by root 30 I minus 1 by root 30 j plus 2 by root 30 k. This is a unit vector in the direction of the given vector A. Unit vector means magnitude 1 unit. So how can you write a vector with magnitude 8 units? This A cap is a vector in the direction of this vector having magnitude 1 unit. What we have to do here, multiplying this vector by 8. So it becomes 40 by root 30 I minus 40 by root 30 j plus, sorry, it is 8 by root 30. 8 5 is 40 by root 30 I minus 8 into 1 it is 8 by root 30 j plus 8 into 2 it is 16 by root 30 k. Is it clear? Now the next one is show that the vectors show that the vectors 2i minus 3j plus 4k, 2i minus 3j plus 4k and minus 4i plus 6j minus 8k are collinear. Collinear vectors means parallel vectors. All scalar multiples are parallel vectors. So here let us write this as A. A is equal to 2i minus 3j plus 4k. Then B equals minus 4i plus 6j minus 8k. This can be written as minus 2 into 2i minus 3j plus 4k. Minus 2 is a common factor here. So it becomes minus 2 into 2i minus 3j plus 4k. This is equal to minus 2 vector A. Vector B is a scalar multiple of vector A. Therefore, they are collinear. Collinear vectors. Can you say what will be the direction of this vector B? Direction of vector B. That will be opposite to vector A because we are multiplying it with a negative number. The scalar here is a negative number. So vector B is having direction opposite to this. But since this is a scalar multiple of vector A, they are collinear. Now the next is find the direction cosines of the vector. Find the direction cosines of A equals I plus 2j plus 3k. Find the direction cosines of vector A equals I plus 2j plus 3k. See, to find the direction cosines of this, first we have to write the unit vector in the direction of vector A. So here modulus of vector A is root of 1 square plus 2 square plus 3 square. And it is 1 by root 14i plus 2 by root 14j plus 3 by root 14k. The unit vector along the vector A is, here it is 1 square plus 2 square plus 3 square, root 14. So A cap is, now this is a vector with magnitude 1. Therefore, the corresponding direction cosines are 1 by root 14, 2 by root 14 and 3 by root 14. One by root 14, 2 by root 14 and 3 by root 14 are the direction cosines. This 1, 2 and 3 are the direction ratios. Now the next one is find the direction cosines of the vector joining the points a1 2 minus 3 and b minus 1 minus 2 1. Directed from A to B. Directed from A to B. So first you have to find vector AB. So 2 points are given here and it is given that directed from A to B. That means initial point is A and the terminal point is B. So it is x2 minus x1, which is minus 2i, y2 minus, it is minus 4j, 1 minus minus 3, which is plus 4k. This is vector AB. Let us represent this as vector A. Then A cap is equal to minus 2 by modulus of vector A is what is modulus of vector A? It is 6. So minus 2 by 6i minus 4 by 6j plus 4 by 6k. A cap is minus 2 by 6i minus 4 by 6j plus 4 by 6k. A cap means this is a vector having magnitude 1. Therefore, the direction cosines are minus 2 by 6, which is equal to minus 1 by 3. Here this is equal to minus 2 by 3 and 2 by 3. These are the direction cosines. One more question. Show that the vector I plus j plus k is equally inclined to the axis OX, OY and OZ. OX, OY and OZ. Show that the vector I plus j plus k is equally inclined to the axis OX, OY and OZ. inclined to the axis OX. That means with the x-axis, what is the angle formed? That's what you have to find. So the vector is given by I plus j plus k. We can find the direction cosines. To find the direction cosines, it is 1 by 1 plus 1 plus 1 root 3 I plus 1 by root 3 j plus 1 by root 3 k. Since this vector is of magnitude 1, the direction cosines are, therefore the direction cosines are 1 by root 3, 1 by root 3, 1 by root 3. Direction cosines are defined by cos alpha, which is equal to 1 by root 3, cos beta, which is equal to 1 by root 3, and cos gamma, which is equal to 1 by root 3. This gives alpha is equal to cos inverse 1 by root 3, beta equals cos inverse 1 by root 3, and gamma equals cos inverse 1 by root 3. Alpha is the angle made by this vector with the x-axis. Beta is the angle made by this vector with the y-axis, and gamma is the angle between vector and z-axis. So all these three are equal to cos inverse 1 by root 3. Therefore, they are equally inclined with the axis. Vector A is equally inclined with OX, OY and OZ. Direction cosines are denoted by L, M and N. L is equal to 1 by root 3, M is equal to 1 by root 3 and N is equal to 1 by root 3. L is defined as cos alpha, M is defined as cos beta and N is defined as cos gamma. Try to do the remaining questions yourself. The next question given in your textbook is to find the position vector of a point R which divides the line segment joining 2 points P and Q whose position vectors are given. You have to take the position vector of P as A and Q as B. Then position vector of R is given by MB plus NA by M plus N. Using that formula, you can find the position vector of R when it is dividing internally in the ratio 2:1. It is then when it is dividing externally in the ratio 2:1 or M is to N, you can apply the formula MB minus NA by M minus N. And then next one is to find the position vector of the midpoint. So for that you can apply A plus B by 2. Vector A plus vector B by 2. And the third, that is 17th question, exercise 10.2. For that, show that the points A, B, C whose position vectors are given form the vertices of a right triangle. Form the vertices of a right triangle. So for that, first you have to find the vector AB, BC and AC. Then find their magnitudes. So I will give you a hint for 17th question of your textbook. Okay, first find AB, then BC, then AC or CA. Then find their magnitudes. Magnitudes of this AB, BC and AC. If this satisfies Pythagoras theorem, then A, B and C are the vertices of a right triangle. Okay, try to do these 3 questions yourself. That is 14, 15 and 15, 16 and 17. 15, 16 and 17 of exercise 10.2. So let us move to the next topic in the next class. Thank you.